Hello, this is a video on assigning oxidation numbers. By this time, you should have opened up this page on oxidation numbers and have your electronegativity table handy. And there is a link to this flow chart for determining oxidation numbers. As you should know by now, oxidation number is a system by which we can keep track of how electrons move through a chemical reaction. If we didn't have elements or substances that shared electrons, we would simply use charges and elements because charges indicate how an element is gaining or losing electrons to form the ions, either cation or anion. However, when you introduce the concept of sharing electrons, and we want to keep track of electrons, who do we assign the electrons in sharing events? Well, to do that, we've created a system, and that new electron accounting system is called oxidation numbers. So, the oxidation number handout, the rules that you see right now are the rules that you would see on or in any chemistry book, no matter what level. They're very good rules, and they explain all the ways in which you need to assign oxidation numbers, including I added one in that a lot of times you don't see is the electronegativity table, which you should have. However, I don't feel that this is the best method to use. I believe a series of questions to answer is a better way of determining oxidation numbers for various substances. Before we get started, I do want to tell you a little bit about the difference between a charge and an oxidation number. It's a mechanical thing. Charges have their signs after the number. Oxidation number, the signs come before the number. And you must always have a positive and negative signs when you do oxidation numbers. And the other major thing that happens is most of the times when you do oxidation numbers, when you draw the chemical formulas, the oxidation numbers sit on top of the element that you're dealing with. And you'll see that in a few minutes. So, like I said before, I don't really like using this table to explain how to determine oxidation numbers. This table is used, I like to use for the exceptions. There are certain elements that have multiple oxidation numbers in there for certain things, and this provides that. What I do like better is to assign oxidation numbers is this flowchart. And this flowchart I made up, so it's not going to be any place. And it's designed not for a set of rules, it's designed around the concept of there's only certain types of substances that we deal with. Elements, ionic compounds, and as from the chemical naming section, you know that I break it up into multiple types of ionic compounds, binary ionic compounds with polyatomics, ionic compounds with cations with more than one charge, and molecular compounds, and of course just polyatomic ions by themselves. So that's what this flowchart deals with, and it basically works off the KISS principle, keep it simple. So you look at the simplest ones first, and then you work your way to harder ones. So, for example, the first question I ask myself is it an element? Okay, if it's an element, then that's under yes. Then you know what the oxidation number is. It's 0, always. If it's not an element, you come down here. The next major question you ask yourself is it a binary ionic compound? And remember, a binary ionic compound is simply a metal that is now a cation and a non-metal element that's now an anion. If that's the case, then yes, then the oxidation numbers are simply the charges, of course changing where the sign is. If it's neither a element or a binary ionic compound, then we get into the sharing of electrons. And with the sharing of electrons, this is kind of like the new material. The first thing you do is you look for the most electronegative substance there is. In that, whatever's more electronegative value, that will have the negative oxidation number. What's the actual number that goes along with the negative sign? Usually the most common charge that you would have for that element. And then the other one is, which is the positive oxidation number. You have to do what they call you sum the oxidation number times the subscript of one element. You multiply those two, and you add it to the same exact thing for the other element or as many elements you have. And you sum them all up, and it's equaling. And here's the little tricky part. It equals, that summation stuff, equals 0 if it's a molecular compound, and if it's a polyatomic ion, it's equal to the charge. And I'll show you an example of each. Doing an example actually is a little bit easier to understand. And then the last one is the most complicated, which incorporates both. Sharing electrons and not, which of course is the ionic compound with a polyatomic ion in it. The polyatomic ion, of course, is the sharing event. There's actually two different ways of doing this, and I'll explain it below. So, first example, CO2. Well, that is an element, so the oxidation number is 0, and that's how it looks. So that's the first example. So all elements work that way. Next one, Mg1Cl2. Well, Mgl1CO2 is not an element, no. It's a binary ionic compound. So therefore, as we said before, if it's a binary ionic compound, the charges are the oxidation numbers. So here are the two charges, and therefore the oxidation numbers are those. Remember, again, oxidation number, the sign goes before the number. Okay? Next one, C1O2, which is a molecular compound. So it's not an element. It's not a binary ionic compound. It's a molecular compound. So you need to go to your carbon and oxygen. You need to go to your electronegativity table. Carbon 2.5, oxygen 3.5. Okay, that's how I got those numbers. You must always use the same electronegativity table, the one I give you. Okay? So you look to see oxygen has the highest electronegativity. It's going to be the negative oxidation number. So therefore it's going to be minus. And the most common charge for oxygen is 2. So it's minus 2. So the oxidation number for oxygen is minus 2. Okay? Now, how do you find the carbon, the positive one? And this is what the summation. So it's C1O2. Carbon, there's one of them, 1, times the oxidation number, which you don't know, which is X, plus there's 2 oxygens, 2, and the oxygen's oxidation number is minus 2, is equal to, because you don't sum anymore because there's nothing else. And now it's equal to, since it's a molecular compound, it's equal to 0. So therefore, when you do the math, X is equal to plus 4. So the oxidation number of carbon is plus 4. So it will look like C1O2 plus 4 minus 2. That's how you would write it. So next example is a polyatomic ion, nitrate. No, it's not an element. No, it's not a binary ionic compound. It's a polyatomic ion down here. Again, you look at the electronegativity table. Nitrogen's 3, oxygen's 3.5. Doesn't have to be always oxygen. Therefore, oxygen is more electronegative, so it's the negative oxidation number, and again, it's 2. Now to find N, you're going to do the same thing. N1O3, 1 minus. There's 1N. Oxidation number is X, plus there's 3 oxygens. Oxidation number is minus 2 is equal to, now it's not 0 because it's not a molecular compound. It's equal to its charge, minus 1. So therefore, x is equal to plus 5. So therefore, again, what will look like is NO3, 1 minus, a plus 5 over an N, and minus 2 over the O. So the last one is the ionic compound with a polyatomic ion. So no, it's not that, it's a special case. So now it gets a little more complicated. So if it's method A, what you do in method A, you break up the compound into its ions. So you have Ca2 plus, NO3, 1 minus. Well, you already know, therefore, what's the oxidation number of Ca. It's going to be plus 2, okay? Because it's a cation, and the oxidation number of a cation is its charge. Now, nitrate, we already did this before. We did this on the polyatomic above, but you do the same exact thing, and you get plus 5 minus 2. The other method of doing it, and this is limited to just 3 atoms. So if you have a polyatomic ion that has 3 atoms in it, like acetate, and it's in an ionic compound, this method B can't work because you have 4 substances. In this method B, you can only have 3, because what you're going to do, as it says here, you look for the least electronegative, which is calcium, which has the positive oxidation number, and the most common one is 2, so it's plus 2. That's why it's plus 2. Oxygen is most electronegative. It's going to have the negative oxidation number, and of course, oxygen, most common oxidation charge is 2, so it's minus 2. Now you find the N, which is in the middle. So again, you do the same exact thing. There's 1 Ca has a plus 2 charge, plus 2, because it's it's 1N times 2, which is 2, times X, which is the oxidation number for N, plus 3 times 2 oxygens is 6, with the oxidation number of minus 2. And since we're dealing with the substance as a complete compound, it's going to equal 0. So when you do the math, you get X is equal to plus 5. So therefore, it's plus 5, which if you look, it's the same exact answer. So therefore, that is done the same exact way. Okay? Again, I think this method is an easier method using this flowchart to explain how to assign oxidation numbers. Do you have to draw out this flowchart all the time? No, it's just how you think when you're doing these. Okay? But you do still need to have memorized the exceptions in this first rules for assigning oxidation number. So give the examples a try and see what happens. Thank you very much.